All right, folks, welcome to day 3 of our functional group extravaganza here in Chemistry 2. I'm trying to pull extra energy since I'm recording this kind of later at night, but here we go. So far we have covered our alcohols and ethers, then we moved on to aldehydes and ketones, and then today we're going to try to tackle carboxylic acids and also esters. And so these will be similar to the aldehydes and ketones in that they're a part of the carbonyl family. So you'll see that characteristic oxygen double bonded to carbon. And so that will kind of follow that same kind of electron density pattern of oxygen at the top, more electronegative, carbon at the bottom, less electronegative. However, what we're also going to see is there's going to be a second oxygen incorporated as well. For the carboxylic acid, that oxygen will be attached to a hydrogen. For the ester, that oxygen is going to be connected to another part of the molecule, kind of similar to an ether. You'll notice these two are kind of stacked on top of each other in our chart. So, without further ado, let's head on over to the notes. All right, so same learning targets, identify them, name and draw them, predict some products, and then at the end, you'll take a look at some real-life applications, which today has to do with mangoes and poison ivy. So I hope you find that interesting. I certainly did. Okay, so basic structure, we kind of just talked through that, so let's draw those in right quick. So your carboxylic acid will be attached to, part of your molecule on one side, so that's our R. You'll have your carbon attached to your oxygen, and then on the other side, you'll have an O, an oxygen attached to a hydrogen. And so your electron-dense regions will be your oxygens, and what that will do is that will make the center carbonyl, that carbon, even more kind of partially positive, since it has both of those oxygens drawing away electron density. Okay. Now, esters, of course, again, look similar. They're connected to one part of the molecule on the left. They'll also have that carbonyl group where you have a carbon attached to an oxygen. They'll have an oxygen as well, and then it will go on into the rest of the molecule on the other side. And so you'll have a similar kind of electron density situation where you've got your more negative oxygens and then your more partially positive carbon region. Okay. So now what we're going to do is practice locating these guys. Got some different compounds for you today. We're going kind of pharmaceutical on these. So your first compound that you're looking at is aspirin, and then your second one is called enalapril, which is a medication kind of used to treat a few different things like high blood pressure, diabetic kidney disease, and sometimes heart failure. So go ahead if you want and pause for a sec, see if you can hunt down those functional groups, and then pop back in and we'll walk through it together. All right, welcome back. Or I guess you technically may not have gone anywhere, but anyways, hopefully you gave it a try. So let's see if we can find those carboxylic acids. So again, what you're looking for is kind of that OH attached to your carbonyl. So there's one in our aspirin. And we also have another carboxylic acid here on the far right of the enalapril. And then our esters, we have a lovely ester here kind of on the end of our aspirin. And we also have another ester kind of on the end of enalapril as well. Okay. And so again, the functional groups are called functional because they're going to give these specific molecules kind of some different roles or different functions. All right. So let's see if we can figure out how to name these guys right quick. And just while I'm thinking about it, sometimes if like a book or a website is trying to save space, they may sometimes, instead of drawing out the full carboxylic acid group, they may just abbreviate it as COOH. And so what that stands for is you've got your carbon there, you've got your 2 oxygens and your hydrogens. So if you see something that looks like COO, then that's just referring to a carboxylic acid. So anyways, just throwing that out there while that was on my brain. Okay, so naming. So when carboxylic acids are the main functional group, it will change the suffix at the end to oic acid. And what goes in front of the oic is the prefix indicating how many carbons you have as a part of the chain. So if you have one carbon, that kind of corresponds to the prefix meth, so it'll be methanoic acid, which is actually the same thing as formic acid. You may have heard that. Ethanoic acid would have 2 carbons, and then the carboxylic acid. It's also called acetic acids, like your vinegar, things like that. Butanoic acid has 4 carbons, and then benzoic acid is attached to a benzene ring. All right, esters, on the other hand, when they are the main functional group, they change the suffix to -ate. And again, what goes in front of the -ate is kind of based off of our normal carbon prefixes, meth, eth, prop, but, pent, kind of so on and so forth. All right. The one thing that's going to change is because esters have kind of 2 sides to them, one side of the molecule and the other side of the molecule, we do need to account for both sides as well. Okay. So here's the way they're going to break it up. Let me zoom in here so we can see just a little bit better. All right. And so I'm going to start with kind of the methyl ethanoate over here, just to kind of show you how the naming works. Let me change my highlighter there. So the methyl group, that is the small group, kind of on the other side of the oxygen of our ester. And then where the eth is coming from is the 2 carbons that are a part of the carbonyl group, and then on the other side. All right. So then if we look at the same thing for the other part of our molecule, we have the bute coming from that long carbon chain, kind of on the carbonyl side. And then the ethyl portion is coming from the other side, where we have the oxygen kind of as a separating barrier. Okay, same thing for methyl benzoate. So here's our methyl group on the right of the oxygen. And then the benzene is what's on the left, kind of on the carbonyl side. So it's methyl benzoate. And then this one, kind of saved this guy for last, but this one happens to have just 1 carbon on either side. So that's where you have the meth kind of repeating twice as your prefix. Methyl methanoate, or methanoate, I guess, technically. All right, so let's give these practice problems a try and see if we can figure out some names. So our first 3 groups that we have are esters, since they have the molecule continuing kind of on the other side of the oxygen there. And so let's go ahead and kind of follow our naming pattern. So let's start by naming the group kind of on the right of the oxygen. So this will be a methyl group. So that's what we'll start our name with. Then we'll consider the other side with the carbonyl to give us the base name for the compound. So the carbonyl side has 2 carbons, which corresponds to eth, so that'll be ethanoate. So methyl ethanoate is our first compound there. Now let's give it a try for the second compound. So on the right of the oxygen here, we have 2 carbons, which in this case is an ethyl group. Then on the carbonyl side, we have 1, 2, 3 carbons, which will go with the prefix prop. So this will be ethyl propanoate, or propanoate if you'd rather say it that way. And then we have our last ester here. So again, on the oxygen side, we have 1, 2, 3 carbons. So we'll start off with propyl. And then on the carbonyl side, we have 1, 2, 3 carbons. And if you'll notice, this last kind of section forms the isopropyl area. So what we're going to do is kind of use that common name. So propyl isopropanoate. Think about my spelling there. So again, we're just taking advantage of that being one of our common kind of little 3-piece parts of our alkane chain. All right, so next on to our carboxylic acids. We're going to practice drawing some of these. And so our carboxylic acid will of course go on the end because it has to have room for an OH group kind of similar to like we did with aldehydes, where we didn't have to number since they'd always be on the end. So what propanoic would mean is that we have 3 carbons total. So we'll need 2 carbons for just the chain and 1 carbon for our carboxylic acid. So we have a total of 1, 2, 3 carbons. Then pentanoic acid means we'll have a total of 5. So 1, 2, 3, 4, 5. And then we can have our carboxylic acid on the end. And we also could have drawn it on from the left, but I guess I just chose to just kind of do it from the right. And now I erased my work, so let me put that back. So 1, 2, 3, 4, 5. Here's our OH, carbonyl. All right. So now, right quick, let's kind of just run through a few reactions that involve carboxylic acids and our esters here. And so one of these we've actually already talked about when we did alcohols, and that is that one of the ways you can synthesize or make carboxylic acids is by oxidizing a primary alcohol using a strong oxidizing agent. So let's pretend that we've kind of got a alcohol with a pretty good sized chain here. And let's pretend that we want to treat it with a strong oxidizing agent, maybe some chromic acid, let's say. And so what will happen is, because this carbon that the primary alcohol is attached to has 2 hydrogens, it can undergo 2 kind of rounds of oxidation, if you will. And what will happen is, at that carbon, we can generate kind of a ketone there, and we can form a carboxylic acid. So we have oxygen kind of double bonded on top, and then we've got the OH group as well. All right. So now what we can do is let's go on and take a look at how we can make some esters. So there are a few different ways that you can make an ester. One of them is by using a substitution reaction, where you can do kind of an SN2 pathway where everything happens in one step. So first, they're using a base like sodium hydroxide to deprotonate or remove the hydrogen from the acid part of the molecule. Then what you're left with is kind of a carboxylate salt, and that just means you have an ion, kind of now, that oxygen with a negative charge. That oxygen can then act as a nucleophile by attacking a part of an alkane chain that's connected to a good leaving group. So in this case, bromine would be your leaving group. The bromine leaves, and then that leaves the oxygen attached to the rest of the molecule. And that's what forms your ester, okay? So that's one way to do it, kind of reusing the substitution pathway. And just kind of to note, and if you use that option, whatever is attached to the leaving group, so I'll put the chain attached to the leaving group, becomes part of the ester. Part of ester. All right. But kind of the main way to make an ester that we're going to focus on is what's called Fischer Esterification. And so what we're going to do is we're going to start out actually use a carboxylic acid, and we're going to combine it with an alcohol to form our ester. Okay. And so notice that it's kind of in the presence of acid as well. Okay. And so what's interesting, if we kind of track the molecules here, we know that ester kind of includes both sides of the molecule. So the side of the molecule on the carbonyl side is going to come from the carboxylic acid, but the other side of the molecule is going to come from the alcohol. Okay. So right quick, kind of a brief little run through of the mechanism. Again, it's already been drawn out here thanks to our lovely online resources. So step 1, since you're in the presence of acid, is to go ahead and protonate that top oxygen of your carbonyl. Again, it's going to be slightly electronegative, so that makes it a good candidate for kind of reaching over to grab that hydrogen from your acid. Then, once that oxygen is protonated, what happens is it creates kind of a positive formal charge on the oxygen. Then what you can do is take the pi electrons from that double bond and move them up to the oxygen to satisfy that positive charge. At the same time, your alcohol is attacking that partially positive carbon, kind of like a nucleophile would. All right. So at that point, your alcohol is attached, but because it still has that hydrogen at the end, it gives this oxygen a positive charge. And so we're going to kind of repeat, what we did earlier, in that we need to remove the hydrogen and give that oxygen some electrons. And so it's not an exact repeat, but kind of following the same theme. So the hydrogen is going to be taken by another one of the alcohol molecules floating around. It will donate its electrons to the oxygen to satisfy that positive charge. And then, here we are. What we're left with is kind of this tetrahedral intermediate where we have the ether here, or the ester here, kind of in progress, not quite an ester yet. So this is the part that came from our alcohol, the part in red. Then the last step, we've got to get back to a carbonyl compound. So we'll have a repeat of the proton transfer where oxygen grabs another hydrogen. And then you'll end up kind of forming a double bond in the end via an elimination reaction. And this is where the water comes from, is it's eliminated as we're reforming this double bond here to create that carbonyl. And then you're left with an ester. And so it's a kind of more, complicated mechanism. So we're not going to, do any problems where we draw that out. But essentially what we need to be able to do is kind of look at a reactant that's a carboxylic acid, the second reactant that's an alcohol, and kind of think about what sort of product will they make. And so the main takeaway is that whatever the carboxylic acid is will stay the same, kind of in the carbonyl side. And then the other side of the ester will come from the alcohol. All right, so let's see if we can predict a few products. We're almost finished here, guys. Okie doke, here we are. So first one right quick. So here's our kind of our carboxylic acid. And so we know that that side of the molecule is going to stay the same. We know that this part will contain our ester. But now what we'll gain from the alcohol is kind of this alkane here that's worth 2 carbons. Okay. And so we'll go ahead and draw that part in. So we've got kind of a 2 carbon stent there, carbon 1 and carbon 2, and that will be our ester. So we have this part from the carboxylic acid, and then this part from our alcohol. And this is still, this oxygen here is from our alcohol as well. So I can highlight, that in the process. There we go. All right, so now let's try this next one here. So we're going to keep kind of our carboxylic acid side over there. We've got a benzene ring that we're attached to. We've got our oxygen, and we're going to gain an oxygen from our alcohol here. And then we've got our alcohol attached to just a methyl group. So we'll just be adding kind of 1 carbon here. And so if we highlight again, we gain kind of the oxygen and methyl group from the alcohol, and the rest of our molecule kind of came from the carboxylic acid. All right, then finally we've got a little ring action over here. So go ahead and draw our 5-membered ring. We're going to keep our carbonyl portion. And then again, we'll take whatever the alcohol gives us. So in this case, it's just another methyl group. All right. So here's our alcohol part. Here's our carboxylic acid part. Okay, so again, just kind of exposing you as how to put these things together. And guys, what we're eventually leading up to is what's called kind of a synthesis process, which is where if you have like kind of a bigger molecule in mind that you need to have certain functional groups, you can take it through a series of these reactions and kind of create, you know, different things that you need. Now, last thing, kind of as a just kind of a fun thing to look at, the Fischer Esterification process can actually happen within one molecule instead of having a separate carboxylic acid and a separate alcohol. And so what you'll notice kind of about this special molecule is it has a carboxylic acid functional group on one end and a primary alcohol functional group on the other end. So it contains both functional groups that we need just within one molecule. And what this allows you to form is kind of a cyclic ester, which is also known as a lactone. And those get used to do lots of kind of neat, interesting things. You can Google those if you want to see some of the applications. But what happens is essentially it's an intramolecular Fischer reaction. And so what happens is if we kind of mark our oxygens here, let me get a different color just right quick. Or I guess I can use the same. Okay, so here's our kind of our ketone here. And these parts are from the ketone. And then we have our oxygen kind of coming from our acid. All right. So if we give this a try just to kind of see how all of this would fold up, essentially what will happen is we're going to have a bond kind of where these two groups are. So essentially this group will be leaving at some point, and this oxygen will now be bonding to this carbon to create an ester. So kind of same thing here, we're bringing the bond to the carbonyl. So if we try to redraw this, we first want to count and see how many carbons we'll have in the ring. So we've got the carbon that's part of the carbonyl, so that's 1, 2, 3, 4. So we should have a ring with 4 carbons and 1 oxygen. So I'll just put our O at the top here. And so that's going to be a total of 5 different members of the group. So we'll go ahead and make our bond to our oxygen. And then I should have 4 carbons. So 1, 2, 3, 4. So there's our ring with kind of 5 different members. 1, 2, 3, 4, 5, our carbon there. And then what's interesting is we've also got kind of a methyl group attached here that's going to be on the carbon closest to the oxygen. So there's our methyl group right there. So here's kind of where we've created that ester part by making the carbonyl right next to that oxygen originally found in our alcohol. So again, just kind of, throwing this out there, showing you what all's out there if you want to, learn more. And so the application article that you'll be reading is kind of similar to yesterday, where it's in a Google Doc that kind of gives you instructions and some questions on it. But you'll be reading about mangoes and how carboxylic acids and esters kind of play a role in that. And it'll also talk to you a little bit about how mangoes have a connection to poison ivy. All right. Well, guys, thank y'all so much for your attention. I appreciate you hanging in there with me all the way. Have a great rest of your Wednesday.